Right now, PSR J0740+6620, a neutron star 3,600 light-years away, is still spinning 200 times every second, crushing more mass into a ball 14 miles wide than scientists thought was physically possible. And NASA has no way to explain why it hasn't already collapsed into a black hole. Not yet, anyway. But here's what nobody is telling you about what happens if it does. A neutron star is what's left after a massive star dies. Its core collapses. Its atoms get crushed together so hard that protons and electrons merge into neutrons. What's left is the densest material we know of. A single teaspoon would outweigh a mountain. Most neutron stars are compact but predictable, about 1.5 times the mass of our Sun, packed into a city-sized sphere. This one sits in the constellation Pegasus. NASA's NICER telescope, mounted on the International Space Station, watched it for years, tracking tiny shifts in its X-ray light as it spins. Then the numbers came back, and they didn't make sense. This neutron star weighs in at 2.14 times the mass of our Sun. That doesn't sound shocking until you remember the size. 14 miles across, smaller than the city of Los Angeles. Almost twice the mass of any neutron star we'd ever confidently measured, compressed into a sphere you could drive across in 15 minutes. Physicists have a name for the point where a neutron star should give up and collapse into a black hole. It's called the Tolman-Oppenheimer-Volkoff limit. Most models place that ceiling around 2 solar masses. This star blew past it, and it's still there, still spinning, still holding together. Every equation said this star should already be gone. It isn't. Something inside it is holding the line against gravity itself, and nobody at NASA can tell you exactly what. The obvious explanation would be a measurement error. Scientists checked, then checked again. NICER's X-ray timing is precise down to the width of a city block, viewed from thousands of light-years away. The mass held up, so researchers turned to the interior. Maybe this star isn't made of ordinary neutrons anymore. Maybe packed at this density, matter breaks down further into a strange soup of quarks, the particles neutrons are built from in the first place. That would explain the extra stiffness needed to resist collapse, but quark matter is still theoretical. Nobody has ever confirmed it exists inside a real star. Teams at Caltech and Harvard have run the models. None of them agree. Here's the part that should worry you more. If this star is this close to the theoretical breaking point, it means the line between neutron star and black hole isn't clean. It's a blur. And somewhere out there, other objects may already be sitting in what astronomers call the mass gap. Too heavy to be a neutron star, too light to be a black hole, according to everything we thought we knew. In 2019, LIGO detected a merger involving an object weighing 2.6 solar masses. Nobody could agree if it was the heaviest neutron star ever recorded or the lightest black hole. That's not a rounding error, that's a hole in physics. And if a small addition of matter, a stray asteroid, a slow trickle from a companion star, pushed this neutron star even slightly further, it wouldn't dim and it wouldn't erode. It would vanish. Instantly. No explosion, no warning. Just a sudden collapse into a black hole, sending out a burst of gravitational waves we might not even be watching for. NASA has no early warning system for this. There is no alarm that goes off when a neutron star gets too heavy. We would only know after it already happened, 3,600 years too late to matter. This changes what we think we know about the densest matter in the universe. If quark matter is real, it means there's an entire phase of physics happening inside these stars that we've never directly observed. A state of matter that doesn't exist naturally anywhere else. Not in any lab, not in any explosion we've built or witnessed. It also means the tools we use to measure black hole mergers, the assumptions baked into gravitational wave astronomy, might be wrong at the edges. Every neutron star we thought we understood could be quietly testing the same limit, and we wouldn't know until one of them crosses it. Some astrophysicists now think the mass gap isn't empty. They think it's full of objects like this one, holding on by a thread we can't see, in places we're not watching closely enough. and every added gram brings it one step closer to a threshold nobody can define. So the question NASA still can't answer is simple. How much more can this star take before it stops being a neutron star at all? And if it collapses tonight, 3,600 light-years away, would we even see it in time to understand what it means? Tell me what you think is holding it together. Note, the title says shorts, but the required 900-word script runs roughly 6-7 minutes at your channel's pacing. That's a long-form video length, not a shorts length. Let me know if you actually want a 150-word shorts length cut of this same hook, or if the title tag should just be dropped.